Before we begin tonight, I want to ask you something simple. Wherever you are right now, under a blanket, in the quiet, maybe with the lights already off, I want you to think just for a moment about what's directly beneath you, not the floor, not the foundation of the building. Further than that, tell me where in the world you're listening from tonight and what time it is where you are. I like knowing that, picturing all these different places all at once, settling into the same kind of quiet. Now, let's go down. Most of us spend our entire lives on top of something we never think about. We walk on it, build on it, grow food in it, bury our dead in it, and almost none of us ever wonder what it actually is beneath the first few inches we can dig with a shovel. Tonight, that's where we're going. Not into space, not outward toward the stars, downward into the one direction humans have explored the least, even though it's the closest direction there is, the ground you're standing on. Let's start close as it gets. If you're inside right now, there's a floor beneath you. Beneath that, a foundation concrete, usually poured into the ground at some point in the past, set, cured, and now simply there, holding everything up without complaint. Beneath the foundation, soil. And soil is one of those things we walk over every day without really seeing. It looks like dirt. It feels like dirt. But soil is, in a very real sense, alive. Threaded through with fungi, bacteria, insects, roots, an entire hidden ecosystem in constant slow motion that took thousands of years to become what it is. A single centimeter of topsoil can take anywhere from decades to centuries to form naturally, layer by layer. Organic material breaking down, minerals weathering out of rock, all of it settling into place with a patience that has nothing to do with human timescales beneath the soil rock. And here's where things start to get interesting, because the rock beneath your feet isn't uniform. It isn't the same everywhere. It has a history, a specific local history, different from the rock under a city 1,000 kilometers away, different from the rock under the ocean floor, different from the rock under a mountain range. The rock beneath you was, at some point, something else. Maybe it was sediment at the bottom of an ancient sea, compressed over millions of years into stone. Maybe it was once molten, cooling slowly underground until it hardened into something dense and crystalline. Maybe it was once a different rock, entirely transformed by heat and pressure into something new, the way coal becomes diamond, except slower and stranger and on a scale that's hard to picture. And beneath that rock, more rock, and beneath that, more still. This is the part that I think people underestimate. We tend to picture the Earth's surface as a kind of skin thin, almost decorative, with something completely different just beneath it. But the crust of the Earth, the layer we live on, is not thin in any way that matters to a human life. In most places, it's tens of kilometers thick. Under the oceans, it's thinner, sometimes only 5 to 10 kilometers. Under continents, it can be 30, 40, even 70 kilometers deep. 70 kilometers. That's the distance some people commute to work, except straight down, through solid rock. And here's the thing that I find genuinely strange. The more I sit with it, in the entire history of our species, every tunnel ever dug, every mine ever sunk, every well ever drilled, we have never come close to passing through it. The Kola super deep borehole in the 1970s, in the far northwest of Russia, near the border with Norway, scientists began an extraordinary project. They decided to drill straight down, not for oil, not for minerals, just to see how deep they could go and what they would find along the way. It became known as the Kola Super Deep Borehole. The project took years, decades actually. Engineers had to solve problems that had never been solved before because no one had ever needed to solve them. As the drill went deeper, the rock got hotter, much hotter than anyone had predicted. The drill bits had to be replaced constantly, worn down by rock that fought back at every meter. By the late 1980s, the borehole had reached a depth of just over 12 kilometers. 12 kilometers. To put that in perspective, commercial airplanes cruise at about 10 to 12 kilometers above the ground. The Kohler borehole went down roughly as far as a passenger jet flies up, and at that depth, something happened that the scientists hadn't expected. The temperature became too much for the equipment, not because the rock was molten, it wasn't, not yet, not at that depth, but because it was hotter than the models had predicted, significantly hotter. The drill bits couldn't survive the conditions. Drilling became impractical, and eventually it stopped. 12 kilometers. That's as deep as humans have ever gone into the earth, in the most ambitious drilling project ever attempted. And here's the number that I think deserves a moment of quiet before we move on. The distance from the surface of the earth to its center is approximately 6,371 kilometers. 12 kilometers compared to 6,371. If you were to scale the entire Earth down to the size of an apple, the Kohler super deep borehole wouldn't even break the skin. We have never gotten past the skin. What 12 kilometers actually looks like. I want to sit with that 12 kilometers for a moment, because numbers like this tend to slide past us. They sound impressive, and then they're gone, replaced by the next number, and we never actually feel them. So let's feel it. 12 kilometers down, the temperature at the bottom of the Kohler borehole was measured at around 180 degrees Celsius. That's hot enough to bake bread. Hot enough that water, if it could exist there in liquid form under that pressure, would be scalding beyond anything you've ever touched. And this is still, geologically speaking, almost nothing. This is still within the crust, the outermost, thinnest, most surface layer of the planet. The part we live on, the part that from space looks like a smooth blue and green skin wrapped around the sphere. At 12 kilometers down, the rock samples that came up were strange. Scientists had expected, based on models of how sound waves travel through rock, to find a specific kind of stone at that depth, a transition into a different rock type, something denser, more uniform. Instead, they found something else, rock that had been fractured, deformed, actually soaked with water that had been trapped inside it for what may have been billions of years, water that had never seen the surface, water older than most of the rock formations we can see and touch and walk on. Ancient water, sealed in stone, 12 kilometers down, waiting, in a sense, for a drill that took decades to reach it. And then the drilling stopped, not because they ran out of curiosity, because the planet at that depth simply became too much for the tools available to handle, the part of the earth we've never touched. Beneath the crust, beneath that 12-kilometer mark we managed to reach, and beneath the tens of kilometers we didn't, is something called the mantle. The mantle makes up the vast majority of the Earth's volume. If the crust is the skin of an apple, the mantle is almost the entire apple itself, the flesh, the bulk, the part that makes up most of what the planet actually is. And no human being, no machine built by humans has ever directly touched it. Not once. Everything we know about the mantle, and we do know quite a lot, comes from indirect evidence. From the way earthquakes send vibrations through the planet, vibrations that travel differently depending on what kind of material they pass through, like sound moving differently through air than through water. From rare volcanic eruptions that bring up small fragments of mantle rock carried to the surface by chance from depths the eruption happened to reach, from laboratory experiments that tried to recreate the pressures and temperatures of the deep earth, squeezing tiny samples of rock between diamonds with enough force to simulate what's happening right now, dozens of kilometers beneath wherever you're lying. The mantle is not liquid, despite how it's sometimes described. It's solid rock, but rock that over very long time scales behaves almost like a thick, slow liquid. It flows, not the way water flows, not the way lava flows, more like the way glass flows if you wait long enough, so slowly that on any human time scale it looks completely solid, completely still, completely unmoving. But it isn't still. It's moving right now beneath you at a pace of a few centimeters per year, about the speed your fingernails grow. And this slow, patient, almost imperceptible movement is the reason continents drift, the reason mountain ranges rise, the reason the map of the world, if you waited long enough, millions of years, would rearrange itself entirely, the continents sliding into new configurations, the oceans reshaping themselves around them. All of that driven by something happening beneath the crust in a layer no human has ever touched, moving at the speed of a fingernail. Caves. We haven't finished mapping. Let's come back up a little, not all the way to the surface, but closer to it, because there's another kind of beneath that I want to tell you about. One that's a little easier to picture because it involves spaces, actual, walkable, explorable spaces beneath the ground. Caves. Most people, when they think of caves, picture something relatively small, a chamber, maybe a tunnel leading somewhere, ending somewhere, with an entrance and an exit and a sense of completeness. But some cave systems aren't like that at all. Some cave systems are so large and so complex that after more than a century of dedicated exploration, we still haven't finished mapping them. The largest known cave system in the world is the Mammoth Cave System in the United States. As of the most recent surveys, more than 676 kilometers of passages have been mapped within it. 676 kilometers of tunnels, underground, connected, and new passages are still being found. Explorers, people who do this as a passion, sometimes as a profession, often both continue to discover sections of the cave that had never been entered before. Not because the cave is infinite, but because mapping a three-dimensional maze in complete darkness, where every passage can branch, fork, double back, connect through other passages in ways that aren't obvious until you're standing in them. That kind of mapping takes a very long time. The first European exploration of Mammoth Cave began in the late 1700s, more than 2 centuries ago, and we are still not done. Think about what that means. A space beneath the ground, large enough that 2 centuries of dedicated human effort has not been enough to fully understand its shape. The deepest cave on Earth. There's a different kind of record too, not the longest cave, but the deepest. In the mountains of western Georgia, the country, not the American state, there's a cave system called Veryovkina Cave. It's part of a region with some of the deepest known cave systems on the planet, caves that descend not horizontally, but almost straight down through limestone that has been dissolving slowly for millions of years. Veryovkina Cave has been explored to a depth of more than 2,200 meters below its entrance. 2.2 kilometers straight down into darkness. Exploring a cave like this isn't like walking into a cavern with a flashlight. It involves ropes, rappelling, climbing back up the same way you came down, sometimes over multiple days, with expedition teams camping inside the cave itself in total darkness, 2 kilometers beneath the mountain above them. And even at 2,200 meters, the cave continues. Explorers have found passages that go further. The bottom, if there's a definitive bottom, hasn't been confirmed. I think about the people who do this, who choose to spend days of their lives in absolute darkness, more than 2 kilometers underground, mapping passages that may never be seen by anyone else, for the simple reason that the passage is there and no one knows what's at the end of it. It's a quiet kind of exploration. No cameras follow them for the most part. No crowds wait at the surface. Just a slow, careful, patient work of going somewhere no one has been before, somewhere that has existed in darkness for longer than any human civilization, waiting for absolutely no one. How we know what's at the core. Here's something that I find quietly remarkable, and I want to walk through it carefully because I think it's one of the most beautiful examples of how human curiosity actually works. We have never been to the center of the earth. We never will not with anything resembling current technology, not even close. The deepest hole we've ever drilled, that 12-kilometer borehole, represents less than 0.2% of the distance to the center. And yet, we know quite a lot about what's down there. We know the Earth has a core. We know that core is made primarily of iron and nickel. We know it's divided into two parts, an outer core that's liquid and an inner core that's solid, even though it's harder than the outer core, because the pressure at the center of the planet is so extreme that it keeps the iron solid, even at temperatures that would melt it instantly anywhere else. We know the inner core is roughly the size of the moon. We know all of this without ever having gone there. How? The answer involves earthquakes and a kind of listening that's not so different in spirit from the radio telescopes that listen to the sky. When an earthquake happens, it sends vibrations, seismic waves through the entire planet. These waves travel outward in all directions, including straight down, through the mantle, through the core, and back up the other side of the Earth, where sensitive instruments detect them. And here's the key. Different types of waves behave differently depending on what they pass through. Some waves can travel through liquid, others can't. Some waves speed up when they pass through denser material. Others slow down by placing seismic monitoring stations all over the world and by recording how the waves from a single earthquake arrive, which ones arrive, when, and from which directions. Scientists can essentially build a picture of the Earth's interior, not by going there, by listening to how the planet itself responds when it's struck. It's a little like understanding the inside of a bell by listening to how it rings. You don't need to cut the bell open. The sound itself, the way it travels, the way it changes, tells you about the structure inside. Every earthquake, in this sense, is a kind of involuntary experiment. The planet rings, and all over the world, instruments listen. And from decades of this listening, thousands of earthquakes, recorded by thousands of instruments, compared and cross-referenced and modeled, we've built a picture of the Earth's interior that we've never directly seen. A picture built entirely from echoes. The heat beneath everything. I want to talk about heat for a moment, because I think heat is one of those things that's easy to take for granted until you really think about where it comes from. The Earth is hot on the inside, not just warm, genuinely, intensely hot. The temperature at the core is estimated to be around 5,000 to 6,000 degrees Celsius. That's comparable to the temperature of the surface of the Sunday. The surface of the Sunday inside our planet. Where does that heat come from? Part of it is left over. When the Earth formed billions of years ago, it formed through countless collisions, smaller bodies crashing together again and again, each collision releasing energy as heat. Some of that primordial heat from the literal formation of the planet is still trapped inside it, slowly, slowly leaking outward. Slowly is an understatement. The Earth has been losing this heat for over 4 billion years, and it still has a very long way to go before it cools significantly. But there's another source of heat too, one that I think is genuinely strange in the best way. Deep inside the Earth, certain elements are radioactive. They decay slowly, releasing energy as they do. This isn't a dramatic process. It's not an explosion, not anything sudden. It's a constant, quiet, almost imperceptible release of energy happening in countless tiny amounts all the time throughout the mantle and crust. And the cumulative effect of all that quiet decay happening continuously for billions of years across the entire volume of the planet is enough heat to keep the interior of the Earth at temperatures that rival the surface of a star. This heat is the reason the mantle can flow slowly the way it does. It's the reason volcanoes exist. It's the reason the magnetic field exists, generated by the movement of liquid iron in the outer core, a kind of enormous, slow, planet-sized generator, running continuously, silently, for as long as the Earth has existed. And it's all happening right now beneath you while you read this, while you sleep. The ground beneath your feet isn't simply solid and inert. It's part of an enormous, slow, ancient engine, one that has been running without pause since before there was anyone to notice it. What deep time looks like in rock. I want to take you somewhere specific now. Not deep underground, but to a place where the deep past becomes visible on the surface if you know how to look for it. There are places in the world, certain canyons, certain cliffs, certain exposed rock faces where you can see in layers an extraordinary amount of time stacked up in front of you like the pages of a book. Each layer of rock represents a period of time when sediment was deposited, sand, mud, the remains of ancient life, and then slowly compressed into stone. Layer after layer, each one taking thousands, sometimes millions of years to form. In some of these places, you can stand at the bottom of a canyon and look up, and the rock above you represents not just years or centuries, but hundreds of millions of years, an almost unbroken record written in stone of a span of time so vast that human history, all of it, every civilization that has ever existed, would fit into the very last sliver at the top, a layer so thin you might not even notice it if you weren't looking for it specifically. I find something quietly humbling about this. Not in a way that makes anything feel less important, but in a way that puts things into proportion. The rock beneath your feet, wherever you are, has a story. A long one, longer than anything you could read in a single lifetime, even if every layer were a book, and even if you spent your whole life reading, and that story is still being written right now, slowly, in sediment settling at the bottom of rivers and oceans, layer by layer, the way it always has material that millions of years from now might be rock and might be exposed somewhere in a cliff face for someone or something to look at and wonder about the quiet indifference of depth. I want to say something now that might sound strange at first, but I think it's actually one of the more comforting ideas in this entire story. Everything we've talked about tonight, the borehole that reached 12 kilometers and stopped, the mantle that flows at the speed of a fingernail, the caves that have taken 2 centuries to map and still aren't finished, the core that glows as hot as the surface of a star, none of it knows that we exist. None of it is waiting for us. None of it is hiding from us. None of it has any opinion, one way or another, about whether we ever understand it. It's simply there, doing what it does, the way it has done for billions of years, and will continue to do for billions more, regardless of whether anyone is listening or drilling or mapping or wondering. And I think there's something deeply restful in that, because so much of what fills our days, the things we worry about, the things we feel urgency about, the things that keep us awake exist in a kind of relationship with us. They respond to us. They depend on our attention, our decisions, our timing. The Earth's interior doesn't. It's the largest, closest, most fundamentally present thing in your entire life. More present than anything else could possibly be, since you're quite literally standing on it right now. As you read this, and it doesn't need anything from you at all. It's just there, patient, ancient, hot, slow, indifferent, in the gentlest possible sense of the word, not cold, not hostile, just not needing anything. And maybe for a few minutes tonight, that's something you can borrow. That same quality, the quality of simply being there, without needing to do anything, without needing to respond to anything, without needing anyone's attention at all. Just present, just existing, the way the mantle exists, the way the deep caves exist in their 2 centuries of unfinished darkness, the way the core exists, glowing quietly, far below, indifferent to the hour, indifferent to whether you're awake or asleep. The 12 kilometers revisited. Let's go back one more time to that number. 12 kilometers, the deepest humans have ever gone. I keep returning to it because I think it deserves to be returned to. Not as a failure, it isn't one. 12 kilometers drilled through solid rock against heat and pressure that destroyed equipment faster than it could be replaced represents an extraordinary achievement. Decades of effort, entire career spent on a single hole in the ground. But it's also a kind of marker, a boundary, the edge of what we've managed to physically reach in the one direction that's always been available to us, always beneath our feet, always the closest unexplored frontier there is. We've sent spacecraft beyond the edge of our solar system. We've placed instruments on the surface of Mars. We've photographed galaxies so distant that their light has been traveling toward us since before the Earth itself existed. And we've drilled 12 kilometers down. I don't say this to suggest one is more impressive than the other. They're not really comparable, and both represent extraordinary human effort. But I think it says something interesting about us, about where our curiosity tends to point. Outward, toward the stars, feels natural, vast, visible, full of light. Downward, into the dark, into the heat, into the slow-moving rock. That's a harder kind of curiosity to sustain. There's no light down there to follow, no stars to navigate by, just darkness and heat and pressure increasing the entire way. And yet, 12 kilometers down, we found water that had been sealed in rock for what may be billions of years. We found rock that didn't match our predictions. We found a planet that, even in its outermost, thinnest layer, the layer we live on, the layer we've had the most access to of anything, still had surprises waiting. What else is waiting in the 6,359 kilometers we haven't reached? We may never know, not directly, not by going there ourselves. But the planet will keep doing what it's doing regardless. The mantle will keep flowing, the core will keep glowing, the heat will keep rising, slowly, from depths we'll never see, warming the rock above it, layer by layer, all the way up to the 12 kilometers we've reached, and the soil above that, and the floor beneath you right now. As you read this in the dark, drifting downward, I want to end tonight by asking you to do something, not literally, just in your mind. A kind of slow downward drift, the way your thoughts might drift right before sleep. Picture the room you're in, the floor beneath you, beneath the floor, the foundation, concrete set in place at some point, now simply part of the ground. Beneath that soil, centuries of slow accumulation, layer by layer, full of quiet, patient life. Beneath the soil rock, solid, old, specific to where you are, with its own history, its own story, written in layers that may stretch back millions of years. Deeper still, rock that's warmer, rock under pressure, rock that 12 kilometers down would be hot enough to bake bread, soaked with water, older than almost anything on the surface. And beneath that, the mantle, vast, slow, flowing at the speed of a fingernail, carrying the weight of everything above it, shifting continents over millions of years in movements too slow for any human to ever witness directly. And at the very center, the core, glowing as hot as the surface of a star, generating the magnetic field that right now invisibly surrounds the entire planet, deflecting particles from the sun, making the surface, your surface, the only one you've ever known livable. All of that beneath you right now, not far away, not somewhere else, directly beneath you in a perfectly straight line, all the way down. It's been there your whole life. It was there before you were born. It'll be there long after, slowly cooling, slowly shifting, slowly continuing the way it always has. You don't need to think about any of this to fall asleep. You never have before. The ground has always simply held you without asking for anything in return. So let it hold you now. Let your thoughts settle, the way sediment settles slowly, gently, layer by layer in the stillness. The earth beneath you is patient. It has been patient for over 4 billion years. It can wait for you to fall asleep. Good night. Welcome back. If you drifted off during the first part, that's perfectly fine. That's what this is for. But if you're still here, still awake, let's keep going a little deeper into tonight's subject. We left off at the center of the earth. Tonight, I want to widen the view a little to talk about the surface again, but in a way that connects it to everything underneath. Because the ground beneath your feet isn't just sitting there, it's moving. It's broken into pieces. And those pieces are doing something that, if you watched it happen on a time scale, you could actually perceive would look less like geology and more like something alive. The puzzle pieces beneath the ocean. Here's something that took remarkably long for people to figure out, considering how obvious it seems once you see it. If you look at a map of the world, a simple one, just the outlines of the continents, you'll notice something. The eastern coast of South America and the western coast of Africa look like they could fit together. Not perfectly, but closely. Like two pieces of a puzzle that have been pulled apart. For a long time, this was treated as a curiosity, a coincidence, something to comment on, maybe, but not something with any deeper meaning. It took until the early 20th century for someone to seriously propose that maybe it wasn't a coincidence at all. That maybe once these continents really had been joined part of a single enormous landmass and had since drifted apart slowly over an immense span of time. The idea was met at first with significant skepticism. Continents drifting, moving across the surface of the planet like enormous rafts. It seemed absurd. There was no obvious mechanism, nothing that could explain how something as massive as a continent could possibly move. It took decades and the development of entirely new ways of studying the ocean floor before the evidence became undeniable. And the evidence came from somewhere unexpected. The bottom of the sea, the mountains no one had seen in the middle of the 20th century, As technology improved, scientists began mapping the ocean floor in detail for the first time. Not just its depth, but its shape, the mountains, valleys, ridges, and trenches hidden beneath kilometers of water, completely invisible from the surface. What they found was extraordinary. Running down the middle of the Atlantic Ocean, roughly following the same curve as the coastlines on either side, there's a mountain range, an enormous one, longer than the Andes, the Rockies, and the Himalayas combined, stretching from near the Arctic almost all the way to Antarctica. And almost no one before this mapping had any idea it was there. This underwater mountain range, what's now called a mid-ocean ridge, turned out to be one of the keys to understanding how continents move, because along the very center of this ridge, new ocean floor is constantly being created. Molten rock rises up from below, cools and solidifies, forming new seafloor that then spreads outward, slowly in both directions like a conveyor belt running in slow motion. The seafloor near the ridge is young, geologically speaking. The seafloor further away, closer to the continents, is older. And the rate of spreading, when scientists finally measured it, turned out to be almost exactly the same rate that the continents appeared to be drifting apart. The puzzle pieces weren't just sitting there coincidentally shaped to fit together. They had actually been connected. And the ocean between them, the entire Atlantic, had been created slowly by this process, growing wider every year by a few centimeters for tens of millions of years. The Atlantic Ocean is, in this sense, still being born right now, a few centimeters at a time. What moves the continents? So what actually causes this? What makes pieces of the Earth's crust, pieces that can be thousands of kilometers across, kilometers thick, and unimaginably heavy, move at all? The answer brings us back to the mantle, that slow-flowing layer we talked about earlier, the one that moves at roughly the speed your fingernails grow. The crust of the Earth isn't one continuous shell. It's broken into pieces, what are called tectonic plates. Some of these plates are enormous, carrying entire continents on top of them. Others are smaller, mostly hidden beneath the oceans. These plates float, in a sense, on top of the mantle below, and because the mantle is slowly moving, heated unevenly from below, rising in some places, sinking in others, in a process not unlike the way water moves in a pot. When it's heated from underneath, the plates riding on top of it move too. Slowly, almost imperceptibly, a few centimeters a year in most cases, less than the length of your fingernail. But multiply a few centimeters by tens of millions of years, and you get oceans opening up. Continents drifting apart, colliding, merging, splitting again. Mountain ranges thrust upward where plates collide head-on. Deep trenches formed where one plate is forced beneath another, sliding down into the mantle, slowly being absorbed back into the planet's interior. It's worth sitting with this for a moment. The ground you're on is not fixed. It has never been fixed. It's part of a plate that has been moving slowly, continuously for as long as the Earth has had a solid crust, which is most of its 4-5 billion year history. The place you're lying right now was somewhere else, once, not very long ago. In geological terms, maybe a few hundred kilometers from where it is now, a few million years back. And it'll be somewhere else again, a few million years from now. Slowly, patiently, without anyone noticing, because no single human life is long enough to perceive it directly. The deepest place in the ocean. I want to take you somewhere now that connects this idea of moving plates to something almost unimaginably deep. In the Western Pacific Ocean, there's a place where one tectonic plate is sliding beneath another, being pushed down slowly into the mantle. And where this happens, it creates a trench, a long, narrow, incredibly deep scar in the ocean floor. This is the deepest place on the surface of the earth. If you could take the tallest mountain on the planet and place it into this trench, its peak would still be more than 2 kilometers underwater. The entire mountain, every bit of it, would disappear beneath the surface, and there would still be ocean above it. The pressure at the bottom of this trench is immense, more than 1,000 times the pressure at sea level. It's the kind of pressure that would crush most submarines instantly, not slowly, not with a warning, but in a fraction of a second, the hull collapsing faster than sound can travel through it. And yet, and this is the part that I find genuinely moving, there is life down there. Not much. Not in the way there's life in a coral reef or a forest or even in the deep but more moderate parts of the ocean, but there is life. Specialized, strange, adapted to conditions that would be instantly lethal to almost anything else on the planet. Some of these organisms have never been seen by human eyes directly, only through cameras, on the rare occasions that anything has been sent down that far. A small number of crude descents have reached the very bottom. A handful of people in all of human history have been to the deepest point on Earth, fewer people than have walked on the moon. It's a place that is, in every practical sense, more remote than space, harder to reach, more dangerous, less explored, and it's on our own planet, filled with our own ocean, created by the same slow-moving plates that are, right now, carrying you at the speed of a fingernail across the surface of the Earth. The caves beneath the ice. Let's go somewhere different now, somewhere cold. There's a continent at the bottom of the world that's almost entirely covered in ice. Most people, when they picture it, imagine a flat, featureless expanse of white, and in many places, that's exactly what it is on the surface. But beneath that ice, sometimes, kilometers beneath it, there's something else. Mountains, valleys, lakes. Yes, lakes. Liquid water deep beneath the ice, kept from freezing by the pressure of the ice above and the heat rising slowly from the rock below. One of these lakes is enormous, comparable in size to some of the largest lakes on the surface of the planet. It sits beneath roughly 4 kilometers of ice, and it has been sealed off from the rest of the world, possibly for millions of years. Think about that for a moment. A lake sealed beneath ice for so long that it may never have been touched by sunlight or by the atmosphere as we know it today in all that time. Whatever exists in that water, if anything does, has been completely isolated, evolving, if it evolves at all, in total darkness, under enormous pressure for a span of time longer than our species has existed. When researchers finally drilled down to reach this water carefully, painstakingly, over years, using techniques designed specifically not to contaminate what might be down there, they found microbial life. Not much, not visible to the eye, but life nonetheless, living in conditions that, until relatively recently, most scientists assumed were simply too extreme for anything to survive. This matters for more than just curiosity about Antarctica, because if life can persist in a sealed, dark, freezing lake beneath kilometers of ice on Earth, it raises a quiet question about other places, other moons, other worlds in our own solar system that have ice on their surfaces and potentially liquid water hidden beneath. The deepest, darkest, most isolated places on our own planet may be the closest thing we have to a preview of what we might find elsewhere. The slow violence of mountains. I want to talk about mountains for a moment because mountains are, in a strange way, evidence of everything we've been discussing tonight made visible. When two tectonic plates collide, not sliding past each other, not one diving beneath the other, but pushing directly into each other. Something has to happen to all that material. It can't simply disappear. It gets pushed upward. This is how the tallest mountain ranges on Earth formed, not through volcanic eruption, not through anything sudden or explosive, but through this slow, grinding, centimeter by centimeter collision continuing for tens of millions of years. And here's something that I think is genuinely strange to consider. The tallest mountains on Earth are still growing right now as you read this. Not quickly, a few millimeters a year, in some cases slower even than the plates themselves move, because erosion is constantly wearing the mountains down. At the same time, the collision is pushing them up. It's a balance, a slow, ongoing tug of war between forces pushing rock upward and forces wind, rain, ice, time wearing it back down. If you could speed up time, if you could watch millions of years pass in the span of a few minutes, you'd see mountain ranges rise like waves, crest, and slowly erode back down over and over in different places as the plates continue their slow collisions across the planet's surface. The rock at the very top of the tallest mountains, in some cases, contains the fossilized remains of sea creatures, marine life, things that lived and died at the bottom of an ancient ocean millions of years ago and were later lifted slowly over an unimaginable span of time to some of the highest points on the planet, the bottom of the sea, at the top of the world. The question of what's still unfound, I want to come back now to something we touched on earlier, the idea that even in the parts of the Earth we've explored the most, the parts closest to us, the parts we've had the longest access to, we're still finding things we didn't expect. This isn't unusual. It's actually the norm. Every year, new species are discovered not in some remote corner of space, but right here on Earth, in caves, in deep ocean trenches, in soil, in places that on a map look completely unremarkable, places that have existed unchanged in any meaningful sense for thousands or millions of years, simply waiting for someone to look closely enough. Some of these discoveries are small, a new species of insect, a new type of bacteria, something that to most people wouldn't seem significant, but some are larger, new cave systems previously unknown, connecting to caves that had been explored for decades, revealing that what seemed like a complete map was only ever a partial one. The honest truth is this: we don't know how much of our own planet remains genuinely unexplored. Not in the sense of unclaimed territory. Almost everywhere on the surface of the Earth has been mapped, photographed, claimed by someone, but in the sense of fully understood, fully known, fully without surprises. The deep ocean, the deep caves, the deep ice, the deep rock beneath that 12-kilometer mark we've never managed to pass. All of it is still, in a very real sense, frontier. Not because it's far away, but because depth, real depth, the kind measured in kilometers of rock or water or ice, is one of the hardest things for a creature like us, built for the surface, adapted to live on top of things rather than beneath them, to actually reach the weight of what's above you and below. Here's something I find quietly fascinating, and I want to leave you with it before we start to wind down for the night. Right now, wherever you are, there's a column of air above you, stretching up, getting thinner and thinner for many kilometers before it fades into the near emptiness of space. That air has weight. It's pressing down on you right now with a force of about 1 kilogram per square centimeter of your body. You don't feel it because you've never experienced anything else. It's simply the baseline, normal, invisible, and beneath you in the other direction there's rock, kilometers of it in most places. And that rock has weight too, an enormous amount of it. The pressure at the bottom of that 12-kilometer borehole wasn't just about heat, it was about the sheer weight of everything above, pressing down layer after layer for kilometers. You exist right now at a kind of balance point between an ocean of air above you, invisible and mostly empty, and an ocean of rock below you, dense and ancient and almost entirely unexplored. Both of them press on you gently, constantly, without you ever noticing. And both of them, in their own ways, are full of mystery, the air full of weather systems and atmospheric rivers, and the thin, fragile layer that makes life possible at all. The rock full of slow-moving mantle, ancient water, heat from the planet's formation, and depths no human has ever reached. You're not just on the surface of the earth. You're between two vast unknowns, one reaching up, one reaching down, and somehow, in the narrow space between them, everything you've ever known has happened. Drifting, again. I want to end this part the way we ended the last one, with a slow drift downward. But this time, I want you to imagine something a little different. Imagine you could sink gently, slowly, without any discomfort, the way you might sink into a very deep, very soft bed down through the floor beneath you, down through the foundation, down through the soil with its centuries of quiet, slow accumulation, down through the rock, layer after layer, each one a record of some period of time stacked up over millions of years, like pages in a book too large to ever finish reading. Down past the 12-kilometer mark, the deepest any human drill has ever gone into rock, that's hotter, under more pressure, holding water that's been sealed away for longer than almost anything on the surface has existed. Down into the mantle, slow, flowing, patient, carrying the weight of everything above it, moving at a pace too slow for any human life to perceive. And finally, down to the core, glowing, as hot as the surface of a star, generating the invisible field that surrounds the entire planet, protecting everything on the surface, including you right now, without you ever having to think about it. All of that beneath you, all of that has always been beneath you. Every night you've ever fallen asleep, it's been there, patient, ancient, slow, indifferent, in the gentlest possible way. It doesn't need you to understand it. It doesn't need you to explore it. It simply continues the way it has for over 4 billion years, and the way it will for a very long time yet. Let that be enough for tonight. Let the ground hold you the way it always has, and let yourself drift slowly, gently towards sleep. Good night. Welcome back. One more time. This is the final part of tonight's journey downward. If you're still with me, settle in a little deeper than before. We're going to slow down even more from here and let things drift toward their close. In the first two parts, we went down through soil, through rock, through the deepest borehole humans have ever drilled, through the mantle to the core, and then back up into the moving plates, the deep trenches, the hidden lakes beneath the ice. Tonight, I want to bring all of that together, not with new facts, exactly, though there will be a few, but with something a little quieter, a way of holding everything we've talked about, the places that don't change. There's something I keep coming back to, thinking about all of this. Almost everything in our lives changes constantly. The news changes, our bodies change, the people around us change, age, move away, come back different. Even the landscapes we think of as permanent cities, coastlines, forests, change more than we usually notice, just slowly enough that we don't see it happening. But some things really don't change, not on any timescale that matters to us. The deep rock, kilometers down, has been essentially the same for longer than our species has existed. The core has been glowing at roughly the same temperature for billions of years. The deepest ocean trenches have held the same crushing pressure since long before there was anything alive to feel it. These places are, in a sense, outside of history, not untouched by time. Everything is touched by time, eventually, even rock, even mountains, but moving so slowly that, from our perspective, they might as well be still. I find something steadying in that, not because it makes our own lives feel less significant, but because it offers a kind of contrast, a reminder that not everything has to be urgent. Not everything has to be moving quickly, changing, constantly, demanding attention right now. Some things are allowed to simply continue, slowly, quietly, for longer than anyone could watch. A different kind of explorer. I want to tell you about the people who do this kind of work, not the dramatic version, but the quiet, ongoing version. There are scientists who spend entire careers studying a single layer of rock, a single cave system, a single deep-sea trench, returning to it again and again over years, slowly building up a picture that no single expedition could ever capture. This isn't the kind of exploration that makes headlines very often. There's no flag-planting moment, no single dramatic discovery that changes everything overnight. It's slower than that. More like tending a garden than planting one, showing up year after year, adding a little more understanding, refining a little more detail, knowing that the full picture might not come together in your own working life. And yet, this is how almost everything we know about the deep earth has been learned, not through single dramatic breakthroughs, but through this kind of patient, repeated, almost quiet attention, borehole by borehole, survey by survey, earthquake by earthquake, each one sending its vibrations through the planet, each one adding a little more to the picture. There's a kind of humility in this work that I think is worth noticing. The people doing it know, going in, that they probably won't see the whole picture, that the questions they're asking might not be fully answered until long after they're gone. And they do the work anyway, carefully, patiently, because the slow accumulation of understanding matters, even if no single person gets to hold the finished result. What the deep earth has already given us before we drift toward the close of this, I want to mention something simple, something easy to forget, because it's so woven into ordinary life that it stops feeling remarkable. Almost everything you rely on every single day came from beneath the surface at some point. The metal in the device you might be listening on, the minerals that went into the concrete beneath the building you're in, the elements that make up your own body, many of them formed inside stars long before the Earth existed, but concentrated over billions of years into the rock and soil of this specific planet, in forms that eventually became part of the food you eat, and then part of you. The warmth in some homes, in some parts of the world, comes directly from heat drawn out of the ground, geothermal energy, tapping into that same slow, ancient heat we talked about earlier, the heat left over from the planet's formation and from the quiet decay of radioactive elements deep below. Even water you might be drinking right now before sleep has, at some point in its long history, been part of the deep cycles of the planet, evaporated, fallen as rain, soaked into the ground, traveled through rock for years or decades or longer before emerging again clean into a glass. The deep earth isn't separate from your life. It's underneath it, literally and otherwise, quietly providing without asking for anything the way it has for as long as there's been anyone here to receive it. The last descent for this final stretch, I want to do the slow drift one more time, but a little differently. Instead of imagining yourself sinking down, I want you to imagine something resting. Picture somewhere far below you a single drop of water, the kind we talked about earlier, sealed in rock for what might be 1 billion years in the deep crust, far beneath any borehole that's ever been drilled. That drop of water has been there, unmoving in the dark, for longer than there have been mountains where there are now plains, longer than there have been oceans in their current shapes, longer than almost anything on the surface has existed in the form you'd recognize. It isn't waiting, it isn't aware, it's just there, held in stone, patient in the only way that matters, which is simply continuing to exist quietly without needing anything. And somewhere above it, through kilometers of rock, through the mantle's slow flow, through the crust, through the soil, through the floor, you're lying here, also in your own way, simply existing tonight, not needing to do anything else, not needing to solve anything or finish anything or understand everything we've talked about tonight in order for any of it to be true. The drop of water doesn't need you to know about it. The mantle doesn't need you to picture it correctly. The core doesn't need you to remember its temperature. All of it continues, regardless, slow, ancient, indifferent, in the gentlest way. And all you need to do tonight is let yourself rest on top of it, the way you always have, the way everyone always has. You're still here. Good. If you fell asleep during the first part, that's exactly what this is for, and you can come back to this whenever you're ready. But if you're still with me, still somewhere between awake and drifting, let's continue. We've already gone a long way down tonight, through the soil, through the rock, past the deepest borehole ever drilled, into the mantle with its slow, patient flow, down to the core, glowing in the dark, as hot as the surface of a star, generating the invisible field that wraps around the entire planet while you sleep. Now I want to widen the view a little, not outward, not yet, but sideways, in a sense, into the parts of the deep earth that don't fit neatly into a single downward line, into the hidden places that exist, not just beneath our feet, but beneath our oceans, beneath our ice, beneath our oldest mountains. Because the earth isn't just deep in one direction, it's deep everywhere. The ocean, nobody mapped. For most of human history, the ocean floor was simply unknown. Not unknown in the sense of we haven't gotten around to studying it yet. Unknown in the sense of genuinely, completely, practically invisible. The ocean surface could be sailed. The shallows near coastlines could be measured carefully with weighted ropes dropped overboard. But the deep ocean, the vast majority of it, stretching for kilometers below the surface in the open sea, was as inaccessible in any meaningful sense as the surface of another planet. People knew it was there. They knew it was deep. Beyond that, almost nothing. The first real attempts to measure the depth of the deep ocean didn't come until the 19th century, and even then, the methods were slow, imprecise, and exhausting. A ship would stop, a weighted line, kilometers long, would be lowered over the side. The crew would wait sometimes for hours while the line paid out until it finally went slack, indicating it had touched bottom. Then they'd haul it back up, measure how much line had gone out, and record the depth, one measurement at a time, in a body of water that covers more than 2/3 of the planet's surface. You can imagine how long it would have taken to map the entire ocean floor this way. The answer, in practice, is that it never happened, not with ropes. It wasn't until the development of sonar using sound rather than rope, bouncing pulses off the seafloor and measuring how long they took to return, that anything like a systematic picture of the ocean bottom became possible. And what that picture revealed, when it finally started to come together in the mid-20th century, was something almost no one had anticipated. The mountains beneath the sea. The ocean floor is not flat. I think most people, somewhere in the back of their minds, picture the deep ocean as a kind of vast, featureless, plain, dark, cold, empty, extending uniformly in all directions. A floor, it isn't. Beneath the ocean, there are mountain ranges that dwarf anything on land. There are plains, yes, vast and almost perfectly flat in places, because fine sediment settles so slowly and so evenly in the deep ocean that it creates surfaces smoother than almost anything nature produces on land. But there are also canyons deeper than the Grand Canyon, volcanoes, ridges, and one particular feature that, when scientists first mapped it properly, turned out to be the single largest geological structure on the surface of the Earth. The mid-ocean ridge system, it runs almost continuously for roughly 65,000 kilometers through every ocean basin, winding around the planet like the seam on a tennis ball, threading beneath the Atlantic, the Pacific, the Indian Ocean, the Arctic. 65,000 kilometers. To put that in perspective, the circumference of the Earth is about 40,000 kilometers. The mid-ocean ridge is longer than the distance around the entire planet. And almost no one had any idea it was there until sonar made it possible to see it. Along the center of this ridge, something extraordinary is happening. Molten rock rises up from the mantle below, pushes through the crust, cools, and solidifies into new seafloor. Then more molten rock comes up behind it, pushing the newly formed seafloor outward, slowly, in both directions, like a conveyor belt operating in permanent slow motion. The seafloor spreads a few centimeters a year, which means that the ocean basins are, in a very real sense, growing. The Atlantic Ocean is wider today than it was last year. It's wider than it was a century ago. 1,000,000 years ago, it was about 20 kilometers narrower. The ocean is young, geologically speaking, young because it's constantly being created at the ridges and destroyed at the edges where it slides beneath the continents. The oldest ocean floor on Earth is only about 200 million years old. Compare that to some continental rocks, which are nearly 4 billion years old. The continents remember the deep past in their ancient rock. The oceans are constantly being renewed. Where the plates dive down, if new ocean floor is constantly being created at the ridges, something has to happen to the old ocean floor at the other end of the conveyor belt. Otherwise, the planet would simply keep getting bigger, and it doesn't. What happens is this: where old ocean floor meets the edge of a continent, it dives, not suddenly, gradually, over millions of years, pulled down by its own weight into the mantle below, where it slowly absorbed back into the heat from which it came. These places where one plate dives beneath another are called subduction zones, and they're responsible for some of the most dramatic features on the surface of the planet. The deepest trenches in the ocean occur where this diving happens, places where the seafloor has been pulled down faster than the surrounding bottom, creating immense, narrow scars that plunge to depths no sunlight ever reaches, no casual current ever stirs. The deepest of these is in the Western Pacific, and it descends to roughly 11 kilometers below sea level. 11 kilometers. If you took the tallest mountain on Earth and placed it at the bottom of this trench, its peak would still be more than 2 kilometers underwater. You could stack nearly 10 Empire State Buildings on top of each other, and the whole structure would still be submerged. The pressure at that depth is more than 1,000 times the pressure at sea level. Not enough to simply compress water. Water doesn't compress easily, but more than enough to make any air-filled structure collapse almost instantly. A human being, unprotected at that depth, would survive for less time than it takes to read the sentence. And yet, life at the limit, this is the part that, when I first really understood it, stayed with me for days. at the bottom of the deepest ocean trenches in conditions that would be instantly lethal to almost any living thing we typically think of. There is life, not flourishing, diverse, reef-like life, not visible from the surface, not accessible in any casual way, but life nonetheless. Microbes living in the sediment, processing chemicals in the complete absence of sunlight, small crustaceans adapted specifically to the crushing pressure. Their bodies built for conditions that would destroy anything that evolved for the surface world. Even fish pale, specialized, moving slowly through the dark. Life found a way into the deepest, most hostile place on our own planet. I think about this sometimes when stories about the possibility of life elsewhere come up, the question of whether conditions on other worlds might be too extreme, too hostile, too far outside what we consider normal for anything to survive there. And then I think about the bottom of the deepest ocean trench on Earth. If life can exist there in complete darkness, under 1,000 atmospheres of pressure, in water just a few degrees above freezing, feeding on chemicals rather than sunlight, then too extreme starts to feel like a phrase that deserves a lot of careful thought before it's applied anywhere. The boundaries of where life is possible turn out every time we look closely to be much further out than we expected. The ice that remembers, let's go somewhere colder. There's a place at the bottom of the world where ice has been accumulating for so long that the layers at the bottom of it are older than almost anything else on the surface of the planet. Not the ice itself, water cycles. Even old ice is made of water molecules that have been part of countless other things before. But the air trapped inside the ice, tiny bubbles, sealed. When each layer of snow was compressed into ice by the weight above it, that air is old. Old in a very specific, very remarkable way. Each bubble contains a sample of the atmosphere from the time it was sealed in. The gases, the dust, the chemistry of the air from that exact moment preserved unchanged, waiting in the dark, deep under the ice, for someone with a drill and enough patience to come and open it up. Scientists have done exactly this. They've drilled down through kilometers of ice, extracting long cylinders of it, and then carefully analyzed the bubbles inside, reading the ancient air the way you might read tree rings, or the layers of sediment in a lake bed, layer by layer, going further and further back in time. What they've found is a record of the Earth's atmosphere stretching back hundreds of thousands of years. Temperature changes recorded in the chemistry of the ice itself. Carbon dioxide levels recorded in the trapped air. Volcanic eruptions recorded in the layers of ash. Even ancient storms preserved in the chemistry of the dust. All of it there, all of it waiting in ice that no light had touched since the day it formed. There's something quietly extraordinary about this idea that time can be preserved this way, that the past doesn't only exist in written records or in the shapes of things, but sometimes literally, physically, as a sealed sample of itself air from a particular morning thousands of years ago, still chemically intact, waiting to be read, what the ice hides beneath it. Now here's where it gets stranger. Beneath the ice, sometimes kilometers beneath it, there are things that even the most careful surface mapping couldn't have revealed. Mountains, valleys, lakes. In Antarctica, hidden under ice sheets that in some places are nearly 5 kilometers thick, there are entire mountain ranges that most people have never heard of because almost no one knew they existed until relatively recently. Some of these peaks, if the ice was somehow removed, would be comparable in height to the Alps. They've been there all along, beneath the ice, unseen, and the lake's liquid water kept from freezing by the pressure of the kilometers of ice above and the slow heat rising from the rock below. These are perhaps the most striking of all. Lake Vostok, one of the largest, sits beneath roughly 4 kilometers of ice in East Antarctica. It's about the size of Lake Ontario. It has been sealed beneath that ice for somewhere between 15 and 34 million years. 15 to 34 million years. To put that in perspective, when that lake was last connected to the surface, the last time its water saw the sky, breathed the open air, or felt the sun, our earliest human ancestors didn't exist. The continents were in slightly different positions. The climate was different. The world was recognizably similar to today's in broad outline, but different in ways that matter. And since then, that lake has just been there, sealed, patient, in the dark. When scientists finally drilled down to it carefully over years, doing everything possible not to contaminate whatever might be inside, they found that the water was still liquid, still a lake in every physical sense. And they found evidence of microbial life, life in a lake sealed from the rest of the world for longer than our species has existed. It makes you wonder, not as a dramatic claim, but as a quiet, genuine question, what else is down there? In the places we haven't reached yet, in the parts of our own planet that remain, in the most literal sense, unexplored. The hidden rivers. There's another kind of hidden water I want to tell you about, one that exists not in dramatic sealed lakes, but everywhere, quietly, all the time. Groundwater, beneath almost every surface on the land, beneath fields, beneath cities, beneath forests, beneath deserts. There is water in the rock, not in rivers, exactly, not in pools, but saturated into the spaces between rock particles, filling cracks and pores, moving incredibly slowly through stone that from the outside looks completely solid. Some of this water moves at a rate of a few meters per year. Some of it moves at a rate closer to a few centimeters per decade. And some of it, water in very dense, very old rock, barely moves at all. It arrived there thousands of years ago, or hundreds of thousands of years ago, or longer, and it's been there since, held in place, not by anything dramatic, but simply by the slow, frictional embrace of rock that doesn't give way easily. In some of the deepest aquifers, underground water reservoirs, the water being drawn up today fell as rain during periods of history that no living person witnessed. Ice ages, civilizations that don't exist anymore, landscapes that have since been entirely transformed. When you drink water drawn from a deep well, you might be drinking rain that fell before your great-great-grandparents were born. Rain that soaked into the ground slowly and has been moving through rock, one slow centimeter at a time ever since. There's something I find deeply peaceful about that. The idea of water that has been patient, genuinely patient, in ways that have nothing to do with effort or choice, but simply with the nature of what it is and where it is for so long, and then eventually arriving somewhere useful, eventually quenching something. The deep earth is full of this kind of patience. The rock that remembers. I want to talk about something that might sound at first like a purely scientific detail, but which, the more I think about it, feels like something more. Rock remembers things. Not the way living things remember. Not with neurons or chemistry or anything resembling what we call memory, but in a different way, through its structure, its composition, its very arrangement of atoms. Rock preserves a record of the conditions it experienced when it formed, the temperature, the pressure, the chemistry of the fluids it formed in, whether it cooled quickly or slowly, near the surface or deep underground, whether it was squeezed by enormous forces over millions of years or left undisturbed, where the ancient seas once covered it, leaving the chemical signature of seawater and its minerals. All of this is written into the rock itself if you know how to read it. And scientists have learned over the past century or so to read it with increasing precision. By analyzing the ratios of certain atoms' isotopes, which are versions of the same element with slightly different weights, you can determine not just what conditions a rock experienced, but when, how long ago it formed, how long it was buried, how long ago it was brought to the surface. This isn't an approximation. In many cases, it's accurate to within a small percentage of the total age, which, when you're talking about rocks that are billions of years old, still means you can date them to within a few million years. We can read the past in rock the way we read the past in written records. Not perfectly, there are gaps, ambiguities, things that remain uncertain, but genuinely, meaningfully. And the record that the rock contains stretches back further than any other physical record we have access to, further than ice cores, which go back hundreds of thousands of years, further than tree rings, further than any human document, any artifact, any monument. The oldest rocks on Earth, rare fragments of ancient crust that somehow survived billions of years of recycling, are more than 4 billion years old. 4 billion years, not as a metaphor, not as an approximation, as a measurement in atoms of actual elapsed time. The past isn't gone. In rock, in ways most people never think about, it's still here. The animals that live in stone. I want to tell you something that the first time I came across it, I genuinely didn't believe. Not as a judgment, just as an honest reaction to something that sounds, on first hearing, impossible. There are bacteria that live in solid rock, kilometers beneath the surface, in conditions of pressure, heat, and complete darkness that, until recently, most scientists assumed were simply incompatible with life of any kind. They don't live quickly. They don't do much by any standard we typically apply to living things. Their metabolism runs so slowly that some of them may divide, reproduce once every few thousand years, not every few thousand minutes, not every few thousand days, every few thousand years. They exist in a kind of biological slow motion so extreme that it barely registers as motion at all. Their entire lives, from one cell division to the next, span time periods longer than recorded human history. And yet, by any meaningful definition, they're alive. They process chemicals, they respond to the environment in whatever minimal way they do. They reproduce, eventually. They are alive in the rock, kilometers beneath your feet, right now, at a pace so slow it makes glaciers look impulsive. I find this genuinely moving, not as a scientific curiosity exactly, but as a kind of reminder that life, whatever it fundamentally is, doesn't require the speed, the warmth, the light, the abundance of any of the things we usually associate with it. It requires almost nothing, it turns out, except the right chemistry and enough time. And in the deep earth, there's an extraordinary amount of time. The sounds the earth makes. Here's something most people never think about. The earth makes sounds, not sounds you can hear in the ordinary sense, not sounds that travel through the air to your ears, but sounds in the scientific sense, vibrations propagating through the body of the planet at frequencies far below the range of human hearing. Some of these are caused by earthquakes, vibrations from the sudden movement of tectonic plates, which travel through the entire planet and can be detected by sensitive instruments on the other side of the world. This is the same phenomenon we talked about earlier, the one that allowed scientists to map the interior of the Earth without ever going there, using earthquakes as a kind of involuntary sonar, the planet ringing like a bell and revealing its structure through the way the sound travels. But there are other vibrations too, smaller, more constant. Not from earthquakes, but from the ongoing motion of the planet itself, the movement of the mantle, the flow of material in the outer core, the slow adjustments happening continuously beneath everything. The earth is never completely still. It vibrates gently, constantly, at frequencies so low they're measured not in cycles per second, but in cycles per hour. These are sometimes called the Earth's hum, a background resonance present all the time below the threshold of anything any human could ever hear, but real and measurable, and in its own way, as constant as gravity. The planet is humming right now. You're resting on something that, in the most literal physical sense, vibrates very gently, very slowly, in a frequency too low for any human sense to detect, but real, coming back to the surface. I want to bring us back up slowly through everything we've passed through tonight, past the core with its ancient heat and its slow ion currents generating the magnetic field that protects the surface, has always protected it for billions of years, without anyone's help, without anyone's awareness. Past the mantle, with its patient, fingernail-slow flow, carrying the weight of continents, drawing tectonic plates apart in some places and driving them together in others, building mountains over millions of years. In the same slow way it tears ocean floors apart. Past the deepest borehole, that 12-kilometer mark, deeper than any passenger jet flies above the ground, deeper than any human has physically gone in any other direction, and into the rock that, even at this depth, still surprised the scientists who drilled into it. Water sealed inside, temperatures higher than predicted, a planet that, even at the very edge of human reach, was not quite what we expected. Past the caves, the ones that have taken 2 centuries to partially map, the ones still being explored today, the ones where underground rivers have been carving passages for millions of years without anyone to notice, past the deep aquifers with their ancient water, past the microbes living in slow motion in solid rock, past the fossils of sea creatures lifted by continental collisions to the tops of mountains, all the way up through the soil with its centuries of quiet accumulation, through the floor beneath wherever you're lying. Back here, back to this room, this moment, the patience of things. I want to offer you something before we reach the end tonight. Not a fact, exactly. More of a thought that I keep returning to when I spend time with subjects like this one. Almost everything about the deep earth teaches the same lesson in different ways. That patience, real patience, the kind that doesn't require any effort because it's simply the nature of the thing being patient, is capable of producing almost anything given enough time. Water, patient enough, dissolves limestone into vast cave systems. Rock, patient enough, flows like a liquid and carries continents across the face of the planet. Heat, patient enough, can transform one kind of stone into a completely different kind of stone. Life, patient enough, finds its way into solid rock 2 kilometers underground and simply continues. None of this requires urgency. None of it requires a deadline or a plan or a schedule. It simply requires time. And the deep earth, more than almost anything else we can actually study and touch and measure, has had an extraordinary amount of time. There's a kind of permission in that, I think, not to be lazy or careless or inattentive, but to remember that not everything meaningful happens quickly. That some of the most significant things that have ever happened on this planet happened so slowly that no single living thing could witness them from start to finish. The continents moved, the mountains rose, the oceans opened, and none of it needed to happen fast to matter. The things we haven't found yet. I want to spend a few minutes here near the end of tonight on something that's easy to overlook. We have found an extraordinary amount in the study of the deep earth, the structure of the interior, the mechanism of plate tectonics, the age of rocks, the existence of life in places no one expected it, the hidden lakes and the ancient water and the slow hum of the planet's own vibration. And we found it all with methods that, looked at honestly, are mostly indirect, mostly inferential. We've never seen the mantle directly. We've never touched the core. We've mapped the ocean floor with sonar, not with eyes. We've read the age of rocks through isotope ratios, not through any direct perception of time passing. Everything we know about the deep earth, we know through a kind of listening, through inference, through the patient accumulation of evidence gathered at the surface from a planet that reveals itself not by opening up, but by the way it vibrates, the way its waves travel, the way its chemistry has recorded what it's been through. And this is both remarkable that we've learned so much this way and a reminder of how much we haven't learned yet. The deep earth contains places no instrument has ever reached, processes that happen at scales and time scales that our tools are only beginning to be sensitive enough to detect, structures possibly that we haven't even thought to look for yet. Every major discovery in the earth sciences, plate tectonics, the structure of the core, the existence of deep microbial life, surprised the people who made it. Not mildly surprised them, genuinely, significantly changed what they thought was possible. There's no particular reason to think the pattern is over. There are almost certainly things beneath us. Right now, things happening, things present, things structured in ways we haven't accounted for yet, that future instruments and future patients will eventually reveal. The planet is not a closed book. It just has most of its pages in languages we're still learning to read. What lies between the depths? One thing that struck me putting all of this together is how much of the deep earth story is a story of connection. Things that seem completely separate, the seafloor and the continents, the mantle and the mountains, the deep ice and the ancient atmosphere, the bacteria in the rock and the ecosystem at the surface are all part of the same system, all connected through processes that work across timescales and distances that make the connections invisible to any single observer at any single moment. The carbon in a tree once lived in the atmosphere. Before that, it may have been locked in rock, released by volcanic activity fed by the slow movement of the mantle. Before that, it may have been part of a marine organism that lived and settled to the seafloor and was compressed into sediment and eventually subducted back into the mantle. The same carbon cycling over hundreds of millions of years through forms that would barely recognize each other if recognition meant anything at the molecular level. You are part of this cycle. The carbon in your body has been part of it for as long as carbon has existed on Earth, which is to say, for almost the entire history of the planet. It has been in the atmosphere, in the ocean, in rock, in other living things, in ways that can't be traced, but that are, in some deep sense, real. You are not separate from the deep earth. You are made of it. A temporary arrangement of material that has been part of the planet's slow, patient systems for billions of years, and will be again after its brief time in this particular configuration has passed. That's not a sad thought, I think. It's a connecting one, a conversation across time. I want to try something near the end of tonight. Imagine for a moment that you could have a conversation, not in words, not in anything so quick, with the rock directly beneath you. Not the floor, the rock, real rock, somewhere beneath the building, beneath the soil, beneath the foundations, the kind of rock that has been there for longer than any human structure on Earth, longer than any city, longer than any civilization, longer than our species, in its current form has existed. What would it say if it could say anything? I think it wouldn't say much, not because there's nothing to communicate, but because rock, if it communicated at all, would do so on timescales that make our conversational pace seem frantic. By the time it finished one sentence, the language would have changed. But if it could compress itself into something brief enough to be heard, I think it might say something like this. I have been here for a long time. I have seen many things change, not directly, not with awareness, but in the way the chemical record of everything writes itself into me over time. I have been squeezed and heated and cooled and tilted and broken and healed slowly over more time than any living thing has ever experienced. And I am still here. Changed, yes. Transformed in places beyond recognition, but still here. You will not be here as long as I have been. But you are part of the same story. You are made partly of things that were once me. And when your arrangement shifts, eventually some of what you're made of will return to things like me. I don't say this to be solemn, just as a fact. The kind of fact that, if you let it settle quietly, might feel less like loss and more like belonging. The final descent, one more time. We've done this twice tonight already. Let's do it one final time, not as a journey exactly, but as a settling, a coming to rest. Feel the weight of your body, the pressure of the surface beneath you, pressing back up against you, because that's what surfaces do. That's what the ground has always done. Pushed back gently, exactly as hard as gravity pulls down, holding you in place, the way it's held everything on this planet in place for as long as the planet has had solid ground beneath the surface that's holding you soil. In some places, the soil beneath a person's body is hundreds of years old in its slow accumulation. The living, breathing, endlessly patient process of dead material becoming earth, becoming the ground from which new things can grow beneath the soil rock. Different in every place, but always old, always with its own story, always carrying in its chemistry the memory of what it has been. Deeper the warmth, the slow increase in temperature as you go down, degree by degree, through rock that gets hotter the closer it gets to the heat source at the heart of the planet. Deeper still the mantle, moving not quickly, not in any way you could detect from a human life, but moving constantly in the slow dance that has been rearranging the surface of the planet for as long as the planet has had a surface. And at the center, the core, the oldest heat, the generated field, the silent, glowing, utterly patient heart of the planet, doing what it has always done in conditions no human will ever experience directly for longer than almost anything we know of has existed. All of that beneath you, right now, while you breathe, the things that stay. I want to end tonight with something simple. There are things that change quickly, things that demand your attention, your reaction, your presence of mind right now. Most of the things that fill a day are like this fast-moving present tense requiring response. And then there are things that don't change quickly. The core of the earth has been at roughly the same temperature for millions of years. The mantle has been flowing at roughly the same pace. The deep aquifers hold water that has been patient for longer than any human institution has existed. These things are not going anywhere. Not tonight, not in any time frame that means anything to the part of you that's trying right now to find its way to sleep. They're simply there, as they always have been, as they will continue to be, and you don't need to do anything about any of it. You don't need to understand the mantle correctly, or picture the core at the right temperature, or remember the exact depth of the deepest borehole. All you need to do is rest on top of it. the way everything is always rested on top of it. The ground will hold you tonight, the way it held you last night, and every night before that, without asking for anything, without requiring anything, without needing you to be aware of it at all. It's been doing this for billions of years. It knows how. The volcanoes that built the world, there's a particular kind of mountain that doesn't grow the way other mountains grow. Most mountains rise because of collision plates pushing into each other, rock crumpling upward under pressure, the slow accumulation of material forced into peaks over millions of years. That kind of mountain is patient in its formation, incremental, built from the outside in. But the volcano is different. A volcano grows from the inside out, built not by pressure from the sides, but by material coming up from below molten rock under enormous pressure, finding a weakness in the crust above it and pushing through, sometimes slowly, in long, gentle flows that add layer after layer over thousands of years, sometimes suddenly in eruptions so violent that they reshape landscapes overnight. Volcanoes are, in the most literal sense, the planet's interior expressing itself at the surface. Every eruption is a small piece of the deep earth, the mantle or the lower crust arriving somewhere it has never been before, being exposed to air, to water, to sunlight for the first time in its existence. The lava that flows down the side of a volcano and cools into rock is rock that hours or days before was part of something kilometers beneath the surface, something no human has ever touched or seen or come close to, something ancient and hot and completely inaccessible. And then it arrives glowing at the surface, and people watch. There's a place in the Pacific Ocean where this process happens constantly, visibly, in a way that makes the Earth's interior feel almost accessible, almost touchable, compared to everything we've been discussing. A chain of islands formed not at the edge of a tectonic plate, but in the middle of one. Beneath these islands, a column of unusually hot material rises from deep in the mantle, what geologists call a hotspot, and melts through the overlying plate as it slowly passes above. The plate moves, the hotspot stays. And so, over millions of years, the plate's movement carries each volcanic island away from the hotspot, and a new island begins to form in the place where the plate now sits above the heat source. The oldest islands in the chain are the furthest from the hotspot, eroded now, worn down, some of them sunk back beneath the waves. The newest is the youngest, still growing, still receiving new material from below. A chain of islands, each one a different age, arranged in a line that records the direction and speed of plate movement over millions of years. The islands are, in this sense, a clock, a record of the plate's journey, written in rock and distance. And beneath the newest, youngest island, the process continues. Magma rising, new rock forming, the island growing, imperceptibly, eruption by eruption, year by year. The earth building something, slowly, without stopping, without needing to. The slow memory of minerals. I want to tell you about a mineral that, in a quiet way, might be one of the most remarkable things on Earth. It's called zircon. It's a crystal small, often microscopic, formed when certain kinds of molten rock cool and solidify. In itself, there's nothing particularly dramatic about it. You could walk past a rock containing zircon crystals and never notice them. But zircon has a property that makes it extraordinary. When it forms, zircon incorporates uranium into its crystal structure but actively excludes lead. This matters because uranium, over time, decays into lead at a known measurable rate. So when you find zircon, you can measure how much uranium is in it and how much lead has accumulated since it formed, and from that ratio, calculate with considerable precision exactly how long ago that crystal solidified. It's a clock built into the mineral itself, set when the crystal formed, running continuously without any mechanism, simply by the natural process of radioactive decay, and accurate in many cases to within a fraction of a percent of the true age. The oldest zircon crystals ever found were in Western Australia. They're more than 4 billion years old, older than almost any intact rock on Earth, preserved in younger rock that formed around them. 4 billion years. Those tiny crystals were already ancient before the first complex life appeared on this planet. They formed when the Earth was still young, geologically speaking, when the crust was just beginning to stabilize, when the oceans may have only recently formed, when the moon was closer and the days were shorter, and the world was almost unrecognizably different from what it is now. And they're still here, still containing in their crystal structure the record of the moment they formed, still yielding to a careful enough analysis the exact age of that moment. The past isn't gone. In zircon, it's frozen, waiting, in crystals small enough to sit on the head of a pin, patient enough to outlast almost anything else on the planet's surface, the earthquakes we don't feel. Most people think of earthquakes as things that happen occasionally, dramatically, in specific places, a sudden shaking, a visible event, something that demands attention precisely because it disrupts the ordinary stillness of the ground. But the earth is almost never still, not really. Every day, somewhere in the world, there are hundreds of small earthquakes. Not small in the sense of insignificant, small in the sense of below the threshold of human perception, too gentle to be felt by anyone standing above them, but real and recorded and meaningful to the people whose job it is to pay attention to such things. There are also, at the other end of the scale, events so large and so energetic that their effects propagate through the entire planet, vibrations that travel not just through the local rock, but through the mantle, through the core, and emerge on the other side of the world, detectable by instruments thousands of kilometers from where the event occurred. When the largest earthquakes happen, the planet doesn't just shake locally, it rings. Like a bell struck hard, it vibrates at specific frequencies determined by its size and internal structure, and those vibrations persist measurably, detectably for days afterward. Scientists have used this ringing to refine their understanding of the Earth's interior. Each large earthquake is a new data point. Each one reveals a little more about the structure of what the waves pass through, the density, the composition, the temperature of the material deep below. Every earthquake is, in this sense, an experiment the planet runs on itself, involuntary, unconscious, but producing, for those equipped to read it, information about the deep interior that couldn't be gathered any other way. There's something I find almost meditative about this when I think about it long enough. The Earth vibrates constantly at frequencies too low for humans to hear, with motions too small for humans to feel, producing information that requires extremely sensitive instruments and years of careful analysis to interpret. All of that is happening right now. Below you, vibrations from earthquakes that occurred hours ago or days ago on the other side of the world, still passing through the planet's interior, still carrying information about what they've traveled through. You are resting on something that is, in a very literal, physical sense, still in motion, still reverberating from things that happened long before you lay down tonight. The ground feels still. It always does. But stillness, it turns out, is something we perceive with instruments far too crude to detect what's actually happening. The Earth is always moving, always vibrating, always in its own way, making sound. Just not sound that any living thing can hear. The oldest living things. I want to take a slight turn and talk about something that exists not beneath the surface, but in it, or at least in the borderland between the surface and what's below. The oldest individual living things on Earth are not the largest or the most famous or the ones most people picture when they try to imagine something ancient. They're trees, specific individual trees, not species-specific individual organisms living right now whose roots are in the ground and whose cells contain somewhere in their growth rings the record of thousands of years of continuous life. There are trees alive today that were already old when certain ancient civilizations were at their height, already centuries old when events we now consider ancient history were unfolding. Trees that have been growing slowly, year by year, adding one ring at a time, since before almost everything we think of as the past had happened yet. What I find remarkable about this isn't just the number, it's what it means for the ground those trees are rooted in. The roots of a very old tree have been in contact with the same soil, the same rock beneath it, for thousands of years, slowly changing that soil, slowly drawing minerals from deeper down, incorporating them into wood and leaf and root, returning them when leaves fall and branches die. A continuous, slow conversation between tree and earth, running for a span of time longer than most human institutions have existed. The ground beneath a very old tree isn't the same ground it was when the tree first took root. The tree has changed it, and the tree has been changed by it. A relationship so slow and so gradual that no single human observation could track it, but real and ongoing, and part of the same patient story we've been following all night. What pressure does to things. Here's something that once I started thinking about it, I couldn't stop thinking about. Pressure changes things, not in dramatic, explosive ways, though it can do that too, but in quiet, slow, permanent ways. It transforms the fundamental nature of materials. Things that are soft at the surface become hard under pressure. Things that are solid become capable of flow. Things that would be one kind of mineral at one depth become a completely different kind of mineral deeper down, where the pressure is higher. Carbon, under the pressure and temperature conditions near the surface of the earth, becomes graphite, soft, dark, the material in pencil lead. Carbon, under the pressure and temperature conditions found deep in the mantle, becomes diamond, the hardest naturally occurring substance we know of. Same element, completely different arrangement of atoms, completely different properties. The difference between graphite and diamond is pressure and time. Diamonds form deep in the mantle, under conditions that would be instantly lethal to any living thing. They're then brought to the surface not by mining, at least not originally, but by rare, violent volcanic events that carry material from deep in the mantle up to the surface faster than the diamond can revert to the more stable graphite form at lower pressures. So when you look at a diamond, any diamond, anywhere, you're looking at something that spent a very long time in the deep mantle, something that was formed under conditions humans have never directly experienced, in a place humans have never reached, and was carried upward by forces that, in geological terms, happened almost explosively quickly. A piece of the deep earth delivered to the surface, changed by pressure into something that at the surface is almost indestructible. There's something in that, in the idea that pressure over time can transform something soft and unremarkable into something extraordinarily hard and clear that I keep returning to. Not as a metaphor, just as a fact, though facts sometimes have a way of feeling like metaphors. The seafloor that disappears, Let's go back to the ocean floor for a moment, into something we touched on earlier but didn't follow all the way through. When oceanic plates dive beneath continental plates, the process called subduction, the oceanic rock descends into the mantle. Slowly, over millions of years, it sinks deeper and deeper, the temperature around it increasing, the pressure increasing, until eventually the rock begins to change, to melt partially, to release the water and other volatile substances it's been carrying, which rise into the overlying mantle and change its properties, lowering its melting point, causing it to melt in ways it otherwise wouldn't. That melted material, buoyant, hot, different in composition from the surrounding rock, rises through the overlying plate and emerges eventually as volcanoes. This is why so many of the world's active volcanoes are found along the edges of continents near subduction zones. The volcanic activity there isn't random. It's the direct consequence of oceanic rock diving into the mantle, releasing its stored volatiles, and triggering melting in the rock above. The same process that builds mountain ranges, the collision of plates, also builds volcanoes along those same edges. And the same material that was once ocean floor, carrying the chemical signatures of deep sea sediment and ancient seawater, eventually emerges transformed in volcanic eruptions that add new material to the continents. The oceanic floor disappears into the mantle, and part of it comes back as lava, as new continental rock, as mountains. The cycle runs continuously, has always run. Material descending into the deep earth, transformed by heat and pressure, and returning to the surface in a form almost unrecognizably different from what it was when it went down. Nothing in the deep earth is ever truly lost, just transformed, just waiting for the next stage of a cycle too long for any human life to witness in full. The quiet oceans of the past. I want to take you somewhere that no longer exists. Not physically, there's no way to go there, but in imagination, which is sometimes the only way to go to places that time has removed. There have been oceans on this planet that no longer exist. Not just ocean basins that have since been replaced by new ones. That happens constantly over geologically long timescales, as old seafloor subducts and new seafloor forms at the ridges, but entire bodies of water, vast and distinct, that once covered parts of the planet and have since completely disappeared. Their floors either subducted or compressed into mountain ranges or transformed beyond recognition. One of them, hundreds of millions of years ago, sat between two land masses that were slowly converging. Over tens of millions of years, as its seafloor descended into the mantle at the margins. Bit by bit, kilometer by kilometer, the ocean closed. The seafloor rose up as the plates compressed, forming the beginnings of what would eventually become a mountain range. And then relatively quickly, in geological terms, the ocean was gone. The two land masses had collided. Where water had been, there was now rock. Where ocean creatures had lived and died and settled to the floor over millions of years, there was now the interior of a continent. The fossils of those ocean creatures are still there, in some cases, compressed into the rock of mountain ranges. Marine fossils found at altitude, evidence of water where there is now only stone and sky. The deep past writes itself into the present in places like this. If you know how to look, the landscape tells you about things that happened long before any human was there to see them. The shape of deep time. We've talked about deep time several times tonight in different ways. I want to come back to it one more time at the end, because I think it's the thread that holds all of this together. Deep time is not just a very large number. It's a different relationship with time itself, a different scale at which things operate, with different rules about what's possible and what isn't, what's fast and what's slow, what's sudden and what's gradual. At human timescales, rock is permanent. Mountains don't move. The shape of the coastline doesn't change. These things are, for all practical purposes, fixed, stable reference points in a world of constant, rapid change. But at geological timescales, none of this is true. Rock is temporary. Mountains rise and are worn back down. Coastlines shift continuously. Oceans open and close. Continents drift across the face of the planet, colliding, separating, rearranging themselves into configurations that would be completely unrecognizable to anyone used to the current map. The key isn't that these things are happening faster or slower than we think. It's that they're operating on a time scale so different from human experience that our intuitions about them simply don't apply. When we say a mountain is permanent, we're right within the span of a human life, or even of recorded history. It is. But that's like a mayfly saying the tree it's resting on is permanent. The mayfly isn't wrong, exactly. It's just that the mayfly's lifespan isn't long enough to see the tree change. We are, in a sense, the mayfly, not in any way that diminishes us, just in the sense that the time scales at which the earth operates are so far beyond our natural perception that we have to actively work to understand them, to build instruments, develop methods, do the careful, patient work of reading the evidence that slow time leaves behind, rather than simply being able to perceive them directly. Deep time is, in this way, one of the greatest achievements of human understanding. Not a discovery in the usual sense, not something that was found in a single moment and then known, but an accumulation over centuries of science, of the ability to perceive time on scales that no human could ever experience directly. We learned to read the past in rock, in isotopes, in the way waves travel through the planet, in the fossils of creatures that lived when the planet was configured completely differently. We extended our perception of time far beyond what any individual life could contain. And the picture we found when we did was stranger and older and more patient and more continuous than anything anyone had imagined. The ground that will outlast us. Here's a thought to carry into sleep with you tonight. The ground beneath you will outlast everything that's built on top of it. Not just the building you're in, everything. Every city that currently exists, every road, every bridge, every structure of any kind. In 1,000 years, most of what has been built in the past century will be gone or changed beyond recognition. In 10,000 years, almost all of it. In 1,000,000 years, even the shapes of coastlines will be different. But the rock will still be there, changed, perhaps slowly eroded, slowly buried under new sediment, slowly transformed by the processes we've been talking about all night, but there, continuous with what it is now, in a way that nothing we build ever is. And beneath that, the mantle, still flowing, the core, still glowing, still generating the field that wraps around the planet and deflects the solar wind and makes the surface livable. All of it continuing, long after any human concern has been settled or dissolved or simply forgotten by time. This isn't a sad thought, I think. It's more like a kind of perspective, a reminder that the ground beneath you is not just a surface to walk on. It's part of something much larger, much older, and much more continuous than anything that happens on top of it. You are, for the moment, part of that something made of material that has been part of the planet for billions of years, temporarily arranged into a form that can think about these things, feel curious about them, lie in the dark, and wonder about the heat at the center of the earth and the water sealed in ancient rock and the bacteria living in slow motion 2 kilometers underground. That capacity for wonder, for lying here at night and thinking about what's beneath you, is itself a product of the same deep processes. Life emerging from chemistry, chemistry emerging from rock and water and heat, heat rising slowly from the ancient core. You are the planet briefly thinking about itself, and then eventually returning to what it was before. That's not loss. It's just the shape of the story. Final sleep sequence extended, and now, one last time, we slow down. The story is told. The deep earth has been described, as well as words can describe something that words were never really built for, something that operates in silence, in darkness, in heat and pressure and timescales, so long they lose the quality of time. All that remains is this: your body, wherever it is, the surface beneath you, holding you in place with the same quiet force that holds every object on the planet in place, gravity, the oldest and most constant thing there is. Beneath the surface, the soil, patient, alive, in its slow way, doing what it has always done. Beneath the soil, rock, your rock, specific to where you are, with its own history, old in ways that make the whole span of human civilization seem like a moment. Beneath that warmth, rising slowly from depths no human has ever reached, and beneath that the mantle, moving at a pace too slow for any living thing to perceive, but real and ongoing and responsible for everything about the surface that seems permanent, the continents, the mountains, the shapes of the ocean basins, and at the center, the core, the oldest heat, the generated field, the quiet, steady, ancient engine at the heart of everything, all of it beneath you. Right now, while you breathe, you don't need to understand it. You never did. It has been beneath every person who has ever lived, and it has never required understanding, just a slow, continuous act of being there. Let your thoughts slow, the way water slows as it moves from a fast-moving river into a deep, still lake. Not stopping, just settling, finding the pace of the deeper thing. Let your breathing become the only movement, in and out, at whatever pace feels natural, whatever pace your body finds, without being told. The earth breathes slowly. On the time scale of a human life, it barely breathes at all. But on its own time scale, continents moving, oceans opening, mountains rising and falling, it breathes. You can match that pace for tonight, or something closer to it than the pace of the day you just came from. Slower, quieter, more settled. The deep earth doesn't need anything from you tonight. It just continues the way it always has, patient, warm, ancient, holding everything on its surface with the same quiet, indifferent care it has always provided. You are on the surface. You are held. You don't need to do anything else. Sleep now. The ground is patient. It will still be here. And so will you. Good night. End.